Hello, my name is Sethatevy Bong, and during my spring 2020 internship at the National Institute of Standards and Technology, I have the opportunity and pleasure to work with Dr. Jason Fox, who is a researcher at the Intelligent Systems Division of NIST. The research which I'm working on is the Computational Assessment of Uncertainty in Measurement on Analysis of Metal Additive Manufacturing Surfaces. In this presentation, I will share what I've been working on during this internship and what I have learned from my 3 months of research. I will start off with introducing additive manufacturing and the problem that we're trying to address and how we accomplish our goals in our research. And finally, I will provide a summary description and where we plan to go from here for our future research. So what is additive manufacturing? AM, or additive manufacturing, is 3D printing. AM is a process of joining materials layer upon layer to make objects from 3D models to a complete part as opposed to the conventional subtractive manufacturing. AM can save time and cost. AM allows manufacturer to build parts with customization in a faster manner. Now, because AM starts with nothing and builds the part by printing one layer on top of another until the part is complete, it produces significantly less waste in comparison to subtractive manufacturing. In short, things that are good for AM are those of high value, low volume parts and areas where customizability is crucial. AM covers numerous materials such as metals, polymers, ceramics, and etc. Application of additive manufacturing has become active in the healthcare and aerospace industry. Within these fields, metal is the most heavily researched material. Such example can be seen in this picture from General Electric Aviation, where they are 3D printing turbine engine parts. Indeed, accuracy and precision of the parts is crucial for the part's functionality. Hence, it is important for us to understand AM surface topography because in the manufacturing systems, surface topography has been used as a measure of quality of parts as a means of inspection. It has direct relationship to the functionality of the part. Presently, there remain a lot of questions of how to best understand AM surface topography because of how complex it is to develop the correlation between surface topography and functions, and this leads us to the problem that I am researching on. The issue is with the steep slopes, significant height variation, and reflectivity alteration are all the things that cause uncertainty in the measurement. Since uncertainty has not been adequately addressed in the metal AM industry, the goal of my research is to investigate the effect of measurement error and bias on the calculation of surface texture parameters. And we're using the surface seen here to carry out the project. On the left, we have the input surface, and on the right, we have the output surface with noise added. So, surface texture parameters are assessed for their sensitivity to the measurement errors. The approach that I and my advisor use for this study is by using MATLAB programs as the simulation. For this research, we created 2 main programs. The first program loads the surface data and then it defines slope and slope filter. For instance, slope interval less than 15 degrees, slope between 15 and 30 degrees, and so on. With this slope filter, we then add noise data into it. The reason for using this filtering mechanism is that there is a hypothesis that noise and error present on the surface are slope dependent. Finally, the program then saved the output file by writing the data as text files. The second program is the reverse engineering of the first program. The saved output files from the first program is being loaded in the new program and averaged to eliminate the noise out and obtain only the surface points. Slope filter is used and a reconstruction surface is plotted to verify the program accuracy. These 5 figures are created based on my first program. These are the surfaces from the previous slide, segregated by slopes. For example, the figure in the upper left is the surface where the slope is less than 15 degrees. To the right of that is when the slope is between 15 and 30 degrees, and so forth. Once we segregate by the slope, we can add noise to these different regions and reconstruct the surface. See here, we have the original surface on the left and an added noise surface on the right. For the purpose of this example, we're using uniform noise, and now we can use these surfaces where we added noise to investigate how they affect the calculation of parameters. Based on the output data, we can calculate aerial parameters per ISO 25178, which is the international standards relating to the analysis of 3D aerial surface texture. There are many parameters, but I'm only going to use SDQ as an example for this work. SDQ is the root mean square of the surface gradient, which has degree as the units. And as you can see how complex it is to calculate SDQ, thus this shows how complex and difficult it is to study the propagation of uncertainty in these parameters. For the statistical distribution, we make assessments based on the uncertainty propagation through the parameters. To analyze the accuracy of the program, we use histograms of the noise data and study the shape of how the noise is being distributed and whether it is distributed alike the expected behavior. This assessment approach that I use follows the Monte Carlo method, where we implemented repetitive assessments of surface data to investigate the uncertainty generated by uniform noise. The idea behind the Monte Carlo simulation allows us to easily estimate the effect of uncertainty on complex parameters. This process is repeated numerous times to yield a histogram that produces information on the standard deviation and also the distribution itself. According to the data that we obtained, this is a graph of the SDQ variation. SDQ is affected by both texture amplitude and spacing. In this data, the parameter SDQ is affected by noise. The average SDQ increases as the uniform noise increases, and we can also notice it by the increases in slopes. In some cases, noise affects some parameters very little, while others are affected to a great extent. In this case of SDQ, we're able to say that SDQ is significantly affected by noise. Whereas this figure on the right is an example of how the resultant noise looks like through the histogram. This is the reverse engineered noise from the second program. So I designed the noise value to be a uniform distribution between positive and negative 1 micrometer, and this looks very close to a uniform distribution. Now, the reason it deviates from that is we're not comparing back to the original file, we're comparing back to the average of all the noise files in this second program. Hence, there is a slight variation in the histogram where the Gaussian distribution is present at the edges. However, the area between -1 and 1 are primarily uniformly distributed. To sum up, the correlation between surface topography and function is very difficult to measure. Hence, if there is a point that is a key takeaway from this presentation, is that noise and error are affecting the surface parameters. Hence, the goal of my research is to develop a tool for everyone to estimate how errors and uncertainty affect AM surfaces measurements. That was the goal, and I have shown that I have accomplished it. So for my future studies, I will use real surface data to obtain better understanding of noise and bias. Based on that, I will develop more sophisticated error models. From there, I will assess effect of uncertainty on more in-depth surface filtering, and I will also investigate the effect of other systematic errors and biases. So this is the end of my presentation. I hope you enjoy it and thank you for watching my video.